Take a circle. Mark many equally spaced points around it. Label them 0, 1, 2, and so on. Now, pick a number, say 2, and connect each point to the one labeled 2 times that number, modular p. And just like that, an image appears, lines waving together into a heart-shaped curve. Change the number to 3. The shape turns into a 3-spike shape. Keep changing the perimeters, and the screen fills with splendid geometric patterns, each more intricate than the last. They look beautiful, but why is it? What determines these beautiful shapes, and especially those delicate inner curves that seem to appear out of nowhere? That question first caught my attention when I watched Masologist's video about these times table circles. He showed the same wonder and ended by saying that no one had yet given a mathematical explanation. So, in this video, let's explore what's really hiding inside these circles. Before we jump into it, let's be more clear about how this forms. There are in total 2 perimeters, P and B. P is the number of points around the circle, and B is the multiplier. Here, the multiplier is 2, meaning 1 and 2 connects, 2 and 4 connects, 10 and 20, which is equivalent to 3 on the circle, connects. My first thought was to start from something familiar. The outer heart-shaped curve we see when the multiplier is 2. Then, that shape is called a cardioid, this famous heart-like shape in mathematics, and mathematicians know a standard way to derive this relationship with the lines using what's called envelope theory. The idea is simple. We can first make a Cartesian plan. Then, each line connecting 2 points on the circle form a family of chords. In the Cartesian plan, we know that we can denote lines as a function of x, y, and with a parameter t, where t represents the tth line in this family of chords. The next line can be denoted as fxyt plus h. We want to find the trajectory of 2 infinitely close line pairs. We see when these lines become closer and closer, which is when h approaches 0, we should clearly get a cardioid. Therefore, we can make this problem continuous and take advantage of this. To calculate the intersection, we put these 2 equations together. Now, we can already calculate the trajectory of the cardioid, but just to make the derivation more elegant, we can subtract the system of equation and divide by an h. This gives us the expression of partial differentiation around t. This second equation, along with the equation fxyt equals 0, enables us to eliminate t and get the expression of the cardioid in the Cartesian plan. To see this method in action, let me walk through the cardioid case more concretely. In the modular times table, when the point n is connected to 2n, it is essentially multiply the angle theta by 2 and connect with 2 theta. On the figure, the starting point can be denoted as 0.1 theta equals a cosine theta and a sine theta. For each point that have an angle theta on the circle, it connected with another point that doubles the original angles to the point at angle 2 theta. And this ending point, 0.2 theta, is equal to a cosine 2 theta and a sine 2 theta. We then find the equation connecting the 2 points, forming one chord, fxy and theta. The next step is to write down the equation of the line through P1 and P2, using the standard two-point formula for a line, and simplifying the geometry and trigonometry. This family of lines can be written in the form fxy theta is equal to cosine 2 theta x plus sine 2 theta y minus 2a cosine theta equals 0. Now, as we've mentioned, I can apply the envelope rule. The envelope, as we've derived, can be calculated by eliminating t of these two equations. The first is fxy theta is 0, and the second is its partial derivative around theta is also 0. So, I now have two linear equations in x and y. Cosine 2 theta x plus sine 2 theta y equals 2a cosine theta, and sine 2 theta x plus cosine 2 theta y equals negative a sine theta. We can either use Cartesian form and eliminate t, or use the polar form. But anyway, solving this equation and then switching to polar coordinates, we see that the algebra simplifies nicely to the romantic expression r equals a plus 1, a times 1 plus cosine theta. Therefore, we deduce that the times table picture when the multiplier is 2 gives exactly the classical cardioid. In fact, if you change the multiplier to 3, you get a two-lobed napioid, and for larger numbers, a general curve called an epicycloid occurs, drawn by a point on a small circle rolling around the larger one. Since epicycloid seems to occur everywhere, let's first be more familiar with this shape. An epicycloid is traced by a point on the small circle, as I've mentioned, that rolls without slipping around the outer circle of a larger fixed circle. As the small circle moves, the chosen point sweeps out a spiky curve whose lobes and curves are entirely determined by the ratio of the two radius. If the two curves have the same radius, the rolling point draws a cardioid. If we let the radius of the smaller circle as 1 and the larger circle as r, then the ratio r divided by 1 is r. Another equivalent form is to consider the epicycloid and the factor of the angle. We denote the angle ratio by k, as we've seen here in the diagram. In this video, k is primarily used since the whole discrete diagram is more similar to the second construction method. If the outer circle is twice as large as the inner one, the curve becomes a napioid with two lobes. For other radius ratios, we get epicycloid with more curves, all described by neat parametric equations in terms of the rotation angle. Overall, the shape of epicycloid is solely determined by the ratio k. Here's some examples of how the epicycloids look at different values of k's. But as soon as I tried to use it for the inner patterns, the algebra cannot explain. In the previous model, we only consider the effect of multiplier b and essentially take the number of points around the circle as infinity, making this discrete problem into continuous. In reality, we see even we keep b constant, changing p will also largely affect the final shape. You see, in the case of multiplier b equals 37, when changing p, the shape varies as dramatic as changing the multiplier b. Another observation is, for example, in the case when p equals 134 and b equals 45, the epicycloid is formed not by lines that are infinitely close, but those exactly have 3 points apart. Thus, the continuous model, when the model only focuses on the 2 adjacent pairs of lines to infinitely close adjacent pairs of lines, no longer capture the discrete jumps of the modular arithmetic. That's why the continuous approximation of traditional envelope theory worked beautifully in the previous case, but failed to explain what was happening inside. But apart from the standard envelope theory and algebraic derivation, what else can we go from here? Maybe we need a better observation on the graph itself. Till now, the basic conjecture is the whole diagram has to be strongly connected to epicycloid generalization of cardioid. Back to the modular times table. If we cannot derive the analytic expression from sketch, maybe we can find how the 2 perimeters P and B relate to the single perimeter of general epicycloid K. This way, we can explain and predict the shape of the modular times table. Wondering a few bit, I randomly fixed the total number of points as 111, for example, and start changing B. We recall that we are connecting the line parts starting with each number x and ending at bx. And we see something very nice. When b is equal to 113, 114, and 115, of course, it would be nice. You can see this. You can pause and briefly think about why. And we see this is exactly the figure when the multiplier b is when the multiplier b is 2, 3, and 4, and when the epicycloid perimeter is 2, 3, and 4. Later, I found that nice things happen when b is near some divisors of p. For example, when b is nearly the half of p, familiar diagrams occur again. When b is from 56, a very nice cardioid occurs. How about 57? Beautiful. But what's that? It turns out to be when k is a fraction, 1.5. Very interesting. How about 58? 2.5. How about 59? 3.5. How about 60? 4.5. It seems that there is a rule. But for the first one, remember the parameter of the epicycloid k and its reciprocal 1 over k are the same epicycloid. Now, the rule becomes crystal clear. The denominator is 2, and the numerator is 1, 3, 5, etc. How about b is nearly a fourth of p, when, in this case, p is equal to 111? When b ranges from 28 to 30, the ratio of the general epicycloid ranges from 1 over 4, 5 over 4, 9 over 4. Perfect. The denominator clearly is the nearest ratio of p over b, and the numerator again follows the rule 1, 5, 9, and so on. In general, we have a conjecture. The key is the ratio of p over b. We define this ratio as n, where n is square bracket p over b, where square bracket denotes the nearest number. Another important factor is the remainder. We denote it as P dash equals B times N minus P. The ratio K, which is the ratio of general epicycloid, which solely determines the shape of the epicycloid, is essentially P dash over N. Perfect. Let's try verify for more random cases when, for example, in this case, where P equals 1111 and B equals 86, we want to find the ratio of the epicycloid. We have N is equal to 1111 divided by 86 to the nearest integer, which is 13. And P dash, according to our formula, is 7. Let's try plot the cardioid K equals 13 divided by 7. 13 over 7. Perfect. Here's some more cases. According to our conjecture, all align perfectly. But there are some cases where the rules does not account for the whole diagram. For example, when P is equal to 222 and B equals to 113. If we use the previous conjecture, we found that N is 2 and P dash is 4. We have K is 4 over 2, which is 2. But this 2 indicates there should appear a cardioid, but a cardioid cannot match the original picture. But can you observe the difference? Somehow, the resulting diagram shows 2 copies of the cardioid. One rotates 180 degrees. By observing more cases, we found that this might relate to the ratio P dash over N isn't coprime, and the greatest common divisor P dash and N is 2. The greatest common divisor indicates the number of copies of the cardioid. Another case is P equals 111 and K equals 3, where B is 39 and 40. P dash is 6 and 9. And now we see 3 copies of the cardioid and napioid rotates around and forms the final diagram. Everything follows so nicely. We now believe this conjecture should be right, and all features in the diagram can be explained. Now that we have this neat rule for the perimeter K and the number of copies, let's prove why it actually works. Keep a simple picture in mind. P points around the circle labeled 0, 1, all over to P minus 1, and each labeled x is connected to Bx modular P. The key idea is to consider the remainder. According to our definition of parameters, we have P dash is equal to Bn minus P, and geometrically, P dash is a small overshot. Now, take any label x. Instead of thinking of x as a single number, using Euclidean algorithm, I split it into x equals n times quotient, nq, plus r, and r is between 0 and n. Now, I look at where x goes under the times table map. We have bx is equal to b times nq plus r is equal to bnq plus br. And because bn is equal to p plus p dash, I can rewrite this as bx is equal to p plus p dash times q plus br. Modular p, the term pq disappears, so I'm left with bx is equivalent to p dash q plus br modular p. Here, q tells me how many times the circle rotates, and r tells me where inside the circle it sits. So, after this operation, any starting points and ending points have the following relationship. The starting point has label x is equal to nq plus r, and the ending point has label bx is equivalent to p-q plus br. To understand the shape of the envelope, it is enough to first ignore the remainder r and look at the determinant term at first. Then, the map reduces to x equals nq, and mapping to bx equivalent to p-q modular p. Recall that we've derived from the case of cardioid from x mapping to 2x. It is equivalent to consider from theta mapping to 2 theta, which forms a cardioid. And similarly, in this case, where the map is from nq to p-q, it is equivalent to consider from theta to p-over-n times theta. And that's why, in the conjecture, we see the epicycloid parameter k is exactly p-over-n. This has already explained why this epicycloid occurs in this diagram. Now that we can explain the shape of the epicycloids, the only thing left is to explain why sometimes there occurs more than one epicycloid. Here, the remainder that we neglected at first is the key. The remainder rotate the single epicycloid that eventually results in multiple rotational copies, and we will dig into this in the next episode. So, from a single question in Massage's video came a clean universal rule. 2 ordinary integers are enough to predict all these mysterious inner envelopes. The hidden geometry of the times table circles is not random at all. It is a family of epicycloid quietly forming the arithmetic of multiplication and division. At the end of this video, I would express my greatest gratitude to Massager and all people playing around this diagram for asking the question and started this spectacular journey.